What we're going to announce today is that Mars is not the dry, arid planet that we thought of in the past. Today we're going to announce that under certain circumstances, liquid water has been found on Mars. Now, to give more of a background on those results, let me turn it over to Mike Meyer. Michael?
Thank you, Jim. For the first time, we have orbital evidence of the agent that has enabled water to flow on the surface of today's Mars. For years, we've had orbital spacecraft imaging valleys, streaks, gullies. All of them looked like water was an agent. It had something to do with forming them, but we didn't have any proof. And it was not until about 4 years ago that we found the active process on Mars today that showed that water was a likely culprit. These are called recurring slope lineae, RSL, for the rest of the press conference to save everybody the trouble of saying recurring slope lineae. These are dark streaks that form in late spring, grow through the summer, and then disappear by fall. However, for 4 years, the scientific community has been unable to explain the waxing and waning of these dark streaks on the surface. During this time, additional observations have helped us determine that a broader distribution of RSL than we expected. We're also finding that they are in expanded latitudes. These observations have narrowed the constraints for how RSL might form, but there have been no evidence for water until now. It is through the multiple spacecraft and the multiple years of observations that we've been able to make this discovery of water on today's Mars. And for further details, I'll turn it over to Dwayne, who will pass it on to our scientists.
Yes, let's pass it on to our scientists in France and at Ames, and let's see what this excitement is all about. You're here first from Alfred McEwen from France, attending the European Planetary Science Conference, and then Luigi Oja. Alfred.
Greetings from Nantes. So I'm going to provide some background on the RSL, and I have to explain why we have such a horrible acronym to deal with here. For us scientists, it's better to have a purely descriptive name. That way we can argue about how these formed and still use the same name. We don't want a name that assumes we understand what these are. So we're stuck with RSL. And so I'm going to give a little background, and then I'll turn it over to Luigi to describe his new results. Could I have the first slide, please? So this first view is the title slide. It gives the title of the paper that's being released today in Nature Geoscience. And this is a perspective view as if we were on the ground. There's actually an orbital image, but we project it as if we're on the ground. And the black arrows there point to the tips of these RSL. They actually begin way up near the tops of this hill here. And they flow down over the bedrock, and when they flow out onto the fans at the bottom, that's where they stand out most distinctly. So these are the features we're talking about. And if I could go to the next view graph, this will show you a little animated GIF that shows you the time sequence of these features. So on the left is a black and white image. This is Pallikier crater, and it's all along the north-facing and west-facing rim of this crater. You can see the black arrows point to many of these on the left. On the right is this animated GIF, and it shows the sequence where these start to form in the early summer. They grow either gradually, very gradually, or incrementally. Then they stop growing and they fade. Then they disappear. They're gone entirely for most of the Mars year. The following Mars summer, new features appear and grow that are very similar. So that's the full sequence of events that we've been observing with HiRISE over the last 4 years or so. And these features are very sensitive to the temperature. They form at different times, at different latitudes on Mars. all related to the seasonal variations at those locations. So they're very temperature dependent, and the darkening and the temperature dependence can be explained if these are seeps of water that seep through the shallow surface layer and darken the very surface layer. But we had no direct detection of water. That was just our best guess as to what these were. If you go to the next slide, this is a global map of Mars, and it shows where we have what we call fully confirmed RSL. As of a couple of years ago, this needs to be updated, but it's the same general pattern. There's 3 regions. One is the southern mid-latitudes. Another is Valles Marineris in particular, and there are a few other equatorial spots. And then in the northern hemisphere, we've seen quite a few of these now in Acidalia planitia. Luju is going to talk about his discoveries of hydrated salts in 3 locations that are marked on here. One is in Valles Marineris, in Coprades Chasm. Another is Palakir Crater, which I showed you the animated GIF for. And then we see them in the central peaks of Hale Crater and Horowitz Crater. And John mentioned the Viking results. Well, Norman Horowitz was the principal investigator on the pyrolytic release experiment on the Viking landers, which was one of 4 experiments searching for life on Mars. They had a negative result, although there may be reasons for that. So then the last slide that I'm going to show you, if you go to the next one, this just shows Mars and its orbit around the Sun. And this is to explain a little bit about why we see these at different times in different places. So Mars is tilted on its axis about 25 degrees, very similar to Earth's tilt on its axis. So it has seasons like Earth. When each pole is pointing towards the Sun, it's summer in that hemisphere, winter when it's pointing away. In addition, Mars has a more eccentric orbit, non-circular orbit than does Earth. So right now we have short and hot southern summers and cooler but longer northern summers. And so we see the RSL in southern summer in the southern hemisphere. We see them actually in northern spring in the northern hemisphere. And in the equator, we see them year-round, but they follow the sun. The slope a particular slope is active in the season when that slope is getting the most sun, depending on how it's oriented. All right. With that, I will turn it over to Luju to explain the new results.
Thank you, Alfred. Good day, everyone. It is truly an honor to be addressing this crowd about our results and discovery. As Alfred mentioned, we have been investigating these narrow streaks on Mars ever since their discovery, mainly to elucidate their formation mechanism. We know from prior investigation that these features form on Mars when the temperature condition is ideal for liquid water to exist on the surface. However, as Alfred mentioned, a key evidence was missing until now, and that was their chemical identity. An excellent way to validate the hypothesis that liquid water plays a key role in the formation mechanism of these dark streaks is via spectroscopy. And this is what I will be talking about in this slide. So if you see in the slide, there's an orbiter shooting rays down, and that's basically what spectroscopy is. An excellent example to illustrate the theory behind spectroscopy is, for example, the reason why leaves look green. Our human eyes can recognize various colors. We can see red, blue, yellow, pink, etc. But the reason leaves look green to our human eyes is because a major component of the leaf, which is the chlorophyll, absorbs all the other lights our human eyes are sensitive to and reflect the green light. In the same way, we can view the surface of Mars in different color, which is what you see in this illustration, both in visible and infrared light, and see how light is absorbed by various minerals on the surface. We have an excellent instrument called CRISM on board Mars Reconnaissance Orbiter, which is what you see in this illustration, and it can observe the surface of Mars at various wavelengths. In this work, what we did was we went to these places where we see these narrow streaks and observed the interaction between light and the surface material to see if there was any spectroscopic evidence to support our liquid water hypothesis. So if we go to the next slide, In the next slide, in this slide, you're seeing an animated 3D fly-through of a peak with dark, narrow streaks flowing out of them. During the summer months, this peak can contain hundreds of narrow streaks. This is the same peak that Alfred was earlier talking about, Horowitz. We looked at the surface using the instrument I described before called QUISM to see if there was any evidence for the liquid water hypothesis. So if we go to the next slide, I can show you some of the results. Here you can see two squiggly black lines, which are our observation from the exact place where we saw the narrow streaks in the previous animation. These squiggly lines, they're called spectra, and you can observe few big dips in them. If you read the x-axis, you can see that there's a big dip around 1.9 microns, which means at that particular wavelength, light is being absorbed by whatever is present on the surface. Additionally, you see the same thing at about 2.14 micron, another deep, which means light is also being absorbed at this wavelength. And there are a few other smaller absorption features we see on the spectra. Now we can go here on Earth, we can go to our laboratory and find out which minerals can absorb light at these specific wavelengths. And I present that result in the colored squiggly lines, and I label it laboratory observations. We found that our observation on Mars is well matched by salts composed of chlorine and oxygen called perchlorates, and especially when they are hydrated. And that is really the key here, the hydration. The fact these salts are hydrated when we observe them means that there's presence of molecular water in their crystal structure. The spacecraft MRO that I was talking before observes the surface of Mars every day at roughly 3 p.m., which is the driest time of the day. So most of the liquid water would have been completely evaporated. However, the molecular water trapped inside the salt structure would be a bit more stable, and that is exactly what we observe here. This means that the source of hydration or the source of molecular water in the crystal structure of the salt itself is either due to these features called RSL or some other processes that created these streaks. Regardless, the presence of hydrated salts in these slopes means that these features are forming due to contemporary liquid water. We see similar spectroscopic signature in few other places around Mars. If we go to the next slide, this is Polytear crater. And you can see arrows pointing to some faded streaks flowing out of the crater wall. This is in a slightly different location in the southern hemisphere of Mars. At this location, actually, we have multiple observations from different times. However, we see the hydrated salts only when these streaks are biggest. At other times, when the streaks are narrow and short, we do not see any evidence of hydration. This, again, just like Horowitz, means that the source of hydration or the source of molecular water in the crystal structure of the salt is either due to the presence of RSL or some other processes that created RSL. Regardless, again, just like Horowitz, the presence of hydrated salts in the slope means that these features are forming due to contemporary liquid water. If we go to the next slide, the presence of perchlorate also has some other big implications for water on Mars. You can see the pure water stability on Earth. For example, if you take a glass of liquid water here on Earth, the water will remain in the liquid form until you hit 0 degrees Celsius, when it will start turning into ice. If the temperature approaches about 100 degrees Celsius, then that cup of liquid water will start boiling, and most of the water will start going into the vapor phase. Next, if we take the same glass of water to the surface of Mars, similar thing will happen. The water will freeze at 0 degrees Celsius, but because of the thin atmosphere of Mars, the water will start boiling as soon as the temperature reaches close to 10 degrees Celsius. Therefore, pure liquid water is highly unstable on the surface of Mars, and this is where perchlorate can help us. Next, consider a water mixed with perchlorate or perchlorate brine. If that happens, then the stability of that salty liquid water on the surface of Mars vastly increases. As you can see in the graphic, the perchlorate brine will remain in a liquid form until we hit negative 70 degrees Celsius, and will not start boiling until it is 24 degrees Celsius. Therefore, the presence of perchlorates vastly increases the stability of liquid water on the surface of Mars. Perchlorate also has one other huge implication for water on Mars. And for that, I'm going to turn it to Mary Beth to explain that.
And thank you, gentlemen. And we will now hear from Mary Beth Wilhelm. We'll go to the West Coast at the Ames Research Center. Mary Beth.
Thanks, Dwayne, and thanks, Luzu. So Luzu discussed the first major implication of our work, which pertains to the increased stability of liquid water on the surface of Mars. I will now discuss the second major implication and then discuss some of the broader significance of our findings. So perchlorate salts have a special capability pertaining to the absorption of atmospheric water through a process called deliquescence. Basically, if the humidity in the Martian atmosphere gets high enough, perchlorate salts will absorb the atmospheric water until the salt dissolves and forms a liquid solution. This is one possibility for explaining the formation of RSL. So this sort of physical process can explain the features that we observed here. The discrete darker patches observed in this image may be formed by deliquescence. It is also possible that the formation of RSL is due to other types of processes in which we won't go into depth on here. Perchlorates have a much higher ability to dissolve in water compared with other salts that we see at the Martian surface. So our observations could also be explained by some other liquid water source dissolving perchlorates that are naturally present in the soil and then later depositing them as a solid in higher concentrations. But again, deliquescence is our favored scenario. So here you see a map of the distribution of perchlorates on Mars. The red triangles indicate places on the surface where perchlorates have previously been detected by rovers or landers. Perchlorate is suspected to be present at both of the Viking landing sites and was found in the northern plains by the Phoenix mission in the late 2000s. Most recently, it was detected at Gale Crater by the Sample Analysis at Mars instrument aboard the Curiosity rover. Our detection of perchlorates at RSL sites are shown here in blue, are the first to be made using data acquired by an orbiter. We have increased the number of known locations of this important resource on the Martian surface, showing that perchlorates are perhaps more widely distributed than previously thought. So to summarize, our findings strongly suggest that these recurring slope lineae are formed by liquid water on present-day Mars. The spectroscopic detection of hydrated perchlorates indicates that this water is briny and not pure. So with that, I'll now discuss some of the broader significance of our findings. So water, as I'm sure many of you have heard us say on multiple occasions, is an essential ingredient for life. Our results may point to more habitable conditions on the near surface of Mars than previously thought. Here, potential habitability by Earth-like microbes is unclear. To assess habitability, we would first need to determine how cold and how concentrated the brine is. But the detection that we've described warrants further astrobiological characterization and exploration of these unique regions on Mars. Finally, water may be an important resource for future human explorers and inhabitants of Mars, and may decrease the cost and increase the resilience of human activity on the red planet. Looking forward, it is imperative for us to further understand the source of these water for these features, as well as the amount. And with that, I'll turn it back over to you, Dwayne, at NASA headquarters.